Of course, before an Astrobee can go somewhere, it needs to know where it is, which can be difficult because not only is space a particularly disorienting place, but ground-based methods like GPS are completely useless on board the International Space Station. A significant improvement to the ability of Astrobee to assess its location and orientation was accomplished by developing a visual-inertial graph-based localization system named Astroloc. The previous localizer for Astrobee was based on the Multi-State Constraint Kalman Filter. Kalman filtering is a statistical analysis methodology that helps to remove errors by predicting a number with a degree of certainty. Then, based on that result, it uses a weighted average to make another estimation. The weighted average is constrained in multiple states, meaning that very unlikely possibilities are eliminated, leading to more accurate predictions. In addition, the computation unit was set up to analyze camera images from the extended Kalman filter to reduce noise. This statistical analysis inputs nonlinear data and outputs a linear approximation that is more likely to accurately predict how objects move through space, and therefore be more representative of the Astrobee's location. The Astrobees were able to successfully complete tasks using these analysis methods, but despite how advanced they are, it still wasn't enough, as the unit often got lost and had to be reset or redocked. This is because when various obstacles impeded its view, lighting changed or its surrounding environment changed, like for example an astronaut moves a box during a sunset, it would confuse the computation process. Map landmarks that the robot used to orient itself were no longer visible, so it had to rely on visual-inertial odometry to locate its position. Visual-inertial odometry is the process of using sequential camera images to determine the distance traveled. The lack of gravity also makes localization more difficult, as when we are lost here on Earth, for example, we may not immediately know which way is north, but we always know which way is down. To get around these challenges, NASA researchers developed Astroloc, which is a monocular visual-inertial graph-based localization system. This graph-based optimization calibrated weighted averages by performing relinearization during each iteration compared to the single linearization point used by EKF-based systems. Other graph-based approaches might have used methods that were too computationally intensive for Astrobee's processing unit, which is roughly about the processing power of a mid-range 2016 laptop, and it still had to run a multitude of processes. To work within this limit, it was decided to make the system monocular, meaning it could use just one camera. The graph-based approach allowed multiple observations and sensor measurements to be incorporated into one place, balancing them all out to provide a more accurate assessment of location. These observations and sensor measurements included visual odometry measurements and sliding window marginalization, which is a form of predictive modeling based on previously attained data. Finally, readings go through a covariance-based sanity checker and a pose history sanity checker. These subroutines eliminate data points that have too much variation and confirm that Astrobee's orientation and position over time is physically possible, which limits the use of outliers and sensor data that are likely incorrect. This new way to interpolate visual imagery in conjunction with the floating robot's inertial measurement unit has proven very successful. By comparing sensor readings to actual position, one can easily see the drastic improvements that can be made in localization when a processing unit is able to assure that it only uses sensor readings that make sense. Astroloc builds upon localization software from several projects, including ROVIO, which stands for Robust Visual Inertial Odometry, developed at the Ames Research Center, the SPHERES project, which stands for Synchronize, Position, Hold, Engage, Reorient Experimental Satellites, also the OFCIS project, Optimized Caius Visual Inertial State Estimator, developed in Switzerland, among many others. Aspects of this process have already been vetted by years of research and application. After simulating and finalizing the team's best iteration of the software, it was time for it to be tested repeatedly on Astrobees in the International Space Station. Astroloc demonstrated significant improvements in position, orientation, velocity, and inertial measurement unit bias estimation compared to the previous localizer, as the difference between ground truthing and localization of the robot have been dramatically reduced. By all metrics, Astroloc's software is a very successful project that has made the Astrobee more reliable and useful for the workers on board the International Space Station. As for the Astrobee self-toss experiments, researchers concluded that in the future, closer scrutiny should be given to the angular and linear velocity of the unit from which the appropriate torque is applied by the joint in addition to the best angle for the gripper to release and capture. The importance of the findings, however, helped to give engineers more options in maneuverability in a zero-gravity environment, so that they are not reliant on one way for the robot to move around. If the fans break down, the unit is stationary and loses its core functionality in providing assistance to ground control and crew members in assessing conditions in all parts of the orbital facility. In the future, robots will need to take on a greater role in operating the Lunar Gateway space station, which is due to orbit the Moon as part of NASA's Artemis project. The space station will not be crewed all 12 months of the year, but science experimentation is planned to take place in their absence. Therefore, robotics in space require much more development in the future as reliability, dexterity, and maneuverability must be improved to ensure future exploration in space. The Astrobee is assisting astronauts as we speak, and NASA regularly invites students to write software for experiments and then watch a video link of the experiments take place in real time. This has proven very successful, as crowdsourcing is an excellent way to acquire free labor and to generate public support that NASA needs to maintain its share of the national budget that elected leaders allocate for it on a yearly basis. As for the failure of the Robonaut project, in the future, hopefully NASA will simplify the internal hardware of the robot to make sections of it more modular and easier to repair. If a problem with the machine can be isolated to an internal partition, perhaps software can alert users to the specific problem, and a spare on board can easily replace the faulty one. The next version can be built with failures expected, and repairs can be quick and simple to execute. The successor to Robonaut 2 is tentatively Valkyrie, which is designed to walk on surfaces, like perhaps the Moon or Mars, but at the time of writing is unable to do so autonomously without being attached to cables. In conclusion, while the Robonaut failed to deliver labor-saving services to the cosmonauts, taikonauts, and astronauts on the International Space Station, it provided extremely valuable insight into not only a better way to build robots for space, but better procedures to address potential failures if and when they happen. The testing for new ways of maneuverability went from a postdoctorate study by one individual at a naval academy in California to a published study backed by a team of researchers to actual testing on board the ISS. Using a simple gripping arm with 2 degrees of freedom proved not to be a novel way to move the device to an intended destination, but future researchers have a jumping-off point to continue new ways to address the challenge. Seeing that the Astrobees are currently more reliable, it is likely that NASA could assign them a greater role. It would seem prudent to consider them to be robotic assistants to assist in extravehicular activities when repairs are needed on the exterior of the space station. In the vacuum of space, the impellers have no air to push around to propel them, so alternative methods of maneuverability are absolutely a challenge that will have to be addressed. The Astrobees, with their software-focused approach to innovation, allowed improvements to be made by researchers on Earth that have significantly improved localization and helped the machines further fulfill their mission to assist workers in space. Just as dogs walked alongside humans as our best friends as we migrated throughout the world and established civilizations, robots will float alongside humans as we migrate throughout space and establish a foothold around the solar system. It is studies like these by academia, space agencies, and industry that have allowed us to push further into places that we've never been before. As we continue to explore space, the knowledge that we earn through these studies will help us survive with humankind's new best friend, robots, by our side.